Hello everyone. Um, so in the last lecture we talked about full bridge isolated buck converters. Now I want to explain another type of buck isolated buck converters, which is the half bridge isolated buck converters. The half bridge isolated buck converters are very similar to the full bridge in terms of operation and also their schematics. Okay, so the circuit is similar to the full bridge, except that two transistors and their anti-parallel diodes are replaced by two capacitors. Okay, so let's look at the circuit diagram, the schematic. Let's try it with this black. Okay, so the capacitor here. Okay, so let's name these Q1, Q2, C1, C2, I1 of T. So remember, it has the magnetizing inductance inside the transformer that I didn't draw this time. I just assume that it's there, and you guys should know about that by now. T1 to N. To N is the transformer ratio. L, C, and R. This is I of T. And this is ID of 3 of T. And the current in the diode. Okay, I forgot the anti-parallel diodes here. Okay. Out. Okay. So by writing the volt-second balance, across the magnetizing inductance, it can be concluded that the average of this node here, the average voltage should be equal to the average voltage of this node here. Okay. Of VQ2 has to be equal to VC2 at steady state. Operation. So why is that? It's because so if we have, oh, do they call this VT? So this is V. Let me write that as V of transformer T. Okay, so now the V of transformer T over 1 is equal to VQ2 minus VC2 TS, therefore VQ2, the average of VQ2 TS is equal to the average of VC2 TS. And if I draw the Q2 waveform, okay, there we go. And let me name this VQ2. VQ2. Okay, so it's equal to VI when Q1 is on. It's equal to VCB or VC2 when Q1 turns off. Then when Q2 turns on again, it's equal to 0 again. Then when Q2 turns off, goes back to VC2. And then it repeats the same procedure. Okay, so writing the average of Q2, I have, if this is d TS over 2, and then this is 1 minus d TS over 2, this is dTS over 2, and again this is 1 minus d TS over 2. And then I can write VQ to equal to VI dTS over 2 plus VI dt. Let's write it like this. VI d over 2 plus VC2 over 2 times 1 minus d. Then plus, again I have VC2 times 1 minus d divided by 2 here, which basically gives me dVi over 2 plus VC2 times 1 minus d. Okay, and then the average of VC2 is equal to the capital VC2, which is the voltage across the capacitor. Right now, from these two, plugging in these two equations, VC2, average of VC2 and average of VQ2 into this equation here, we can have dVi over 2 plus VC2 times 1 minus d is equal to VC2. Right, so VC2 goes by VC2, and then therefore dVi over 2 is equal to dVC2. Therefore Vi divided by 2 is equal to the voltage across the capacitor and the voltage across C1. Right? So the voltage that this capacitor and this capacitor sees, the C1 and C2 sees here in the schematic here, is half of Vi, both of them. Okay, so now let's draw the current waveforms. It's very similar to the full bridge waveform that we had before. So how do I toggle this? Okay, so if this is the magnetizing current, this is the transformer voltage, the output current in the inductor, the output voltage before the inductor, after the diodes, and the current in the diodes. So similar to before, Okay. Right. So in here, when Q is on, the voltage the current in the magnetizing inductance of the transformer increases, and then when it turns off, it remains constant, and when it turns off, and when Q1 turns on, Q2 turns on, the current drops and then goes back to the same value that IM was before. Okay, and so the transformer is here would be okay. So here it was 0.5 VI. Here we had the transformer voltage as 0, and then here we have minus 0.5 VI. It's very similar to the full bridge. I don't think we need to explain further on how this works. So IT is the voltage is the current in our output inductor, so which is something like this. And then Vs (0.5 N VI), because so we have 0.5 of VI here, so the transformer ratio is N times, so the Vs that we have here, oh, I forgot to put Vs, so Vs is here, would be N times that value that we had at V of t as the transformer voltage. This is 0, and this is 0.5 NVI again. Then this is 0. So ID3 is equal to whatever value our I of t was above here. So it's an increasing value that it's a linear ramp up, but I draw it as it's identical to the value of the current in the inductor. And then when Q1 turns off, half of the current passes through D3 and half of it passes through D4. So that's going to be like that. And then in the other part, ID3 would be 0, and ID4 would be equal to the current I that is going through the output inductor or the buck inductor. And then 0.5 again. Very similar to the full bridge converter that we have before. Okay, so one important thing to know about this is that the magnitude of Vt of t, which is the transformer voltage, input voltage, is half as large as in the full bridge. Configuration. with the result of an output voltage of V out equal to half of NVI. The factor 0.5 can be compensated by the transformer ratio, by doubling the transformer ratio. However, this causes increased transistor currents, basically double the transistor current. So the benefit of using a half bridge over a full bridge would be that, so we are eliminating two transistors, but what we're doing is that instead of using 4 transistors, we're using 2 transistors, but these 2 transistors have to be able to burden double the current for the same power level that for both applications in the full bridge and half bridge. So if you use half bridge, the transistors that you use have to be able to burden much more currents. So that's the main difference between these two configurations.